Hello everyone, my name is Theo Lombard. I'm doing a PhD at the Laurentian University, working on the footprint of major deformation zone in along greenstone belt, like near Archean greenstone belt. And today I will present a part of my work on the quartz texture and some preliminary work on the pyrite chemistry across the footprint of the Wabigoon and the Larder Lake Cadillac Deformation Zone, so respectively in Dryden and Val-d'Or. So just a little bit of context before that. So my project aimed to document the footprint of different sections of deformation zone, showing the fluid rock interaction in the Archean greenstone belt. So to do that, I'm comparing two different areas with similar geological settings and similar structures, but with really contrasting gold endowment. So we have the first area, which is the Val-d'Or segment along the Larder Lake Cadillac Deformation Zone, which is my enriched gold zone, and then I have my poorly undone gold zone, which is the Dryden segment along the Wabigoon Deformation Zone. So the objective of this study, we have multiple objectives. First, define some elemental gain and losses, so some making some mass balance calculation, and look at different mineralogical change related to the fluid rock interaction. Then identify some specific quartz texture and pyrite texture and trace element signatures associated still with the fluid pathway. Then try to investigate if there is a geothermal gradient associated with the fluid pathway. And finally, combining all of these to try to find some key parameters allowing the differentiation between undone and barren deformation zone. So why do we compare the Val-d'Or area and the Dryden area? Like I said, we have really similar geological settings. We have some mafic volcanic rocks that are above that we have some deep marine turbidites rocks. So in Val-d'Or will be the Pontiac, in Dryden it will be the Thunder Lake groups. And I just put the Timiskaming here and some alluvial here, but I don't have them in my area, but they are present also in the Abitibi. If we look at the deformation stage and some of the gold events, we can see that there is similar gold events in both of the area, mainly around 2660, around 2640, and then late overprint by hydrothermal. Late hydrothermal overprint around 26 or 2590. So for the Val-d'Or area, we have three deformation events: the D1, D2, which is the main deformation event where we reach the green-schist metamorphic peak, and then D3 that will remobilize some of the former structure. For Dryden, we have two main deformation events. There is a third one also, but they don't really record any gold events or impact any gold events. So we have D1, D2, which is reactivating some of the structure of D1. So I went to the field, I collected some samples. So my sampling strategy was to try to take samples on both sides of the main fault zone, to try to see if we have some kind of trend going through the fault zone. So on the right part here, you have the Dryden maps with the Wabigoon Deformation Zone here. You have the former Van Horn prospect here, which was a former mine. And then you have just here the Flambeau Lake area, which is now in exploration. On the right part here, you have the Val-d'Or area, with the Cisco mine here, the Kina mine here, and the Goldex mine just here. So my study is mainly focused on the mafic volcanic rocks, the cross-cutting dikes, and the sedimentary rocks, because this is the main rock type that I found in the area. And I tried to sample different type of veins, so the early quartz carbonate veins and the late QTC vein, quartz to marine veins. So the main rock types in Val-d'Or, all of the rocks have been metamorphosed at the green-schist fasces, but I just removed the prefix meta because it's easier. So first we have the mafic volcanics rocks, commonly occurring as a pilobasalt or massive basalt. They are quite fine grains. They can be some disseminated pyrite. Sometimes the pillows have epidote earth. Then we have the sedimentary rocks, so the Pontiac in Val-d'Or, which consists of mudstone-siltstone alternance. Same, it can be some disseminated pyrite in the most altered part. And then something interesting is that as we are going southward in the Val-d'Or area, you will increase your metamorphism, going from the biotite to the garnet to the storlite shales. And finally, you have some diuretic dikes that cross-cut the mafic volcanics rocks. Those are plurimetric dikes. They can be some epidote, some albitization in the most altered part, and then some disseminated pyrite or pyrrhotite. So similar for Dryden, we have the mafic rocks that are commonly pilobasalt or massive basalt, a bit less fine-grained than in Val-d'Or. Can be also a lot more magnetite, but you still have some pyrite, pyrrhotite, and epidotes in the altered parts. Then you have the sedimentary rocks from the Thunder Lake group. Again, a mudstone-siltstone alternance with some disseminated pyrite in some part. And this time you will increase your metamorphism by going northward, but the metamorphism is much more faster than in Val-d'Or. It's only on 1 or 2 kilometers. And then you have some QFP dikes that cross-cut the metavolcanic rocks. And again, you can have some albitization, pyrite in the most altered zones. So now let's look at the quartz texture. So to do that, I use quartz cathodoluminescence because this method will reveal some texture that are not that you cannot see with other regular imaging, such as microscope or just regular SEM imaging. So if we look at those two pictures, you have the SEI imaging and you have the BSE imaging. And you can see that your quartz is quite homogeneous. We don't see any zonation, but when you start to look at the CL imaging, you will start to see some textures, giving you information about the history and some of the composition of the quartz in terms of trace element. For quartz, the CL imaging is mostly triggered by aluminum, titanium, and lithium. So the more of these three you will have in your quartz, the higher CL intensity you will get usually. So I will just show you quick some of the texture so you can have an idea about what it looks like, and then I will resume everything in a table. So in Val-d'Or, we have at least 3 generations of quartz. One that is really low intensity here, that are considered as primary quartz. Then you have those more light intensity and more molted texture, sometimes homogeneous, that are probably related to some metamorphic quartz, because when you metamorphose the quartz, you will tend to homogenize it and to melt it a little bit and reprecipitate it again. And finally, you have those really light intensity along fractures on the edge of the quartz, which is just due to dissolution and reprecipitation of the quartz along the edge and the fractures. So in Dryden, some of the texture are similar, but first we see this really nice oscillatory zoning. Those ones are quite rare in the area, and this is probably some well-preserved primary quartz. Then we have some mosaic textures, really homogeneous, some molded texture again, some more homogeneous textures, and again along fractures. Here, you will have some reprecipitation, dissolution and reprecipitation. And also, we have these really nice round concentric textures, also along the edge of the grain or in the fractures. So if we combine every observation I did in the area for the quartz carbonates and quartz tourmalines carbonate veins, we can see that most of the texture in the area are just like homogeneous or molted texture until probably to the metamorphism. However, some of the homogeneous texture can still be like maybe considered as primary quartz, because when quartz precipitate has really stable condition, you will get like a really homogeneous quartz. But like most of the texture are found like in both of the rock types, so the texture are not controlled by the rock types and in both of the veins, except for the oscillatory zoning that are only found in dikes in Dryden. So now let's look at the pyrite chemistry. So I did some WDS and EDS imaging before doing some laser ablation. So in Val-d'Or, I found mainly like two types of pyrites. So the primary pyrite, which is euhedral to subhedral, as you can see here, that has like a strong zonation in cobalt and nickel. And that could be like sometimes really porous, as you can see here. They are found in both like QTC and QC veins. And then you have the secondary pyrites that generally overgrow the primary pyrite, but that can occur also alone in association with some chalcopyrites. And those pyrites are subhedral to anhedral, and they have a lack of zonations. For Dryden, similar again, we have the primary pyrite that has like this time a more weak nickel and cobalt zonation, and found like disseminated in the host rock or like in veins. And then you have the secondary pyrite that overgrowth, like here, for example, the primary pyrite that occurs alone also, and that have a lack of zonation, except for some of them, they have a rim enriched in arsenic. So that's really preliminary. So I tried to look at, I did some laser ablation. I tried to look at all of the pyrite first all together. And what I noticed is that most of the pyrite are arsenic poor in both of the area. So for Val-d'Or, you have the empty round circles. And for Dryden, you have the empty round circles. And for Val-d'Or, you will have these triangle shapes. And then you have the rock types for the colors here. So pyrite are arsenic poor. Some elements such as zinc, molybdenum, silver, tungsten, lead seems to have higher concentration in sediments, for example. So they seems to be like a host rock control in terms of the pyrite chemistry. Then I saw that there is a positive correlation between some elements such as tellurium, molybdenum, and silver with gold. And finally, the gold content is not really correlated to the proximity of the deformation zone. So when I plot my points on the map, I saw that most of the pyrite enriching gold are not located directly on the main deformation zone, but more like on secondary or tertiary space of these deformation zones. However, arsenic, tungsten, and cobalt are much more higher when you are going proximal to the deformation zone, and this is consistent with the mass balance that I did and that I showed in a previous talk. So finally, I just want to talk a little bit about the geothermometry of the pyrite and by using the selenium. So I read this article written by Keith and Al. And in this paper, they are talking about the selenium and the tellurium in the pyrite. And they show that the selenium is not fractionated during the fluid boiling or the rock sulfidation, that it's not controlled by the oxygen fugacity and the pH. So they conclude that the selenium is mainly a function of the temperature, and that you can use the selenium to estimate the temperature of the precipitation for the pyrite by using this equation that they give. So basically what they did is that they found a correlation between temperature and selenium and showing like a negative correlation. Well, however, we need to be careful with this geothermometer, because like I tried to use it, But it's really dependent on the accuracy of your analysis for the selenium, and also on the regression line that they found, and also on the R squared of their regression lines, which is quite low. So here's some of the results. I averaged the temperature for some of the pyrite to present it to you. So basically what we have is that we have a temperature that match more or less with orogenic gold deposits in the area. There is no clear gradient in terms of as we are going away from the major deformation zones. However, what I saw is that the primary zone pyrites show constantly higher temperature than the second pyrites. Also, the pyrite temperature is not really correlated with the metamorphism, because as you are going south in Val-d'Or, for example, you're supposed to have, if it was correlated with the metamorphism, you're supposed to have higher temperature of pyrite formation, but it's not the case here. And I wanted to mention also that in Dryden, we have a really, really high temperature for some of the points, and that may be due to magmatic pyrite related to some of the dikes that crosscut the area. So just to conclude, for the quartz, the most common texture is an homogeneous or slightly melted quartz, typical from orogenic or metamorphic quartz. We have rare oscillatory zoning found in Dryden, and there is evidence of quartz dissolution and remobilization along the edge of the grain zone and the fractures, but this is probably not related to the gold events. Finally, like none of the quartz texture are restricted to a specific rock type or vein set. For the pyrite, we have in the two areas, primary pyrite and secondary pyrites. The primary pyrite is euhedral to subhedral, have a well-zoned nickel and cobalt zonation, and they may be porous. The secondary pyrite is subhedral to anhedral, like they have a lack of zonations. Some of the trace elements in the pyrite may be host rock dependent. The higher grade content of gold is not really related to the main fault zone, but more to the secondary place. However, tellurium, molybdenum, antimony, and nickel are. And considering by looking at the temperature, maybe in Val-d'Or there is a weak thermal gradient, but it needs to still to be more. We still need to investigate this more. And in Dryden, we have really high temperature in the Flambeau Lake areas. So just for the future steps, I did some mass balance calculation. Now I'm trying to include some literature data, as you can see here, to have a more widespread data set to do my mass balance. And I would like to do more analysis, such as more like CL quartz imaging, to try to find more of this primary zone quartz. And I would like to go back to the laser, especially for the quartz, because for now I couldn't succeed ablating the quartz. So if you have any ideas about that, give me a clue. So the quartz is really important to confirm the selenium geothermometer, because we will be able to relate the titanium in the quartz with the selenium content in the quartz and use the Titanic-Q geothermometer. And yeah, finally, I will compare my mass balance calculation with the pyrite and quartz chemistry and see if everything is matching well. So thank you for listening to me, and if you have any question, we can talk.